Okay, so this is problem number 4 on exercise. The principal tensile stresses at a point across two mutually perpendicular planes are 100 Newton per millimeter square and 50 Newton per millimeter square. Okay, the principal tensile stresses at a point across two mutually perpendicular planes are 100 Newton per millimeter square and 50 Newton per millimeter square. So the situation is as such. In this cross section there are two stresses. Sigma 1 is 100 Newton per millimeter square, perpendicular direction. This is sigma x, this is sigma y. Okay, 50 Newton per millimeter square. Determine the normal, tangential and resultant stresses on a plane inclined at 30 degree to the axis of minor principal stress. The question is, find out the normal, tangential and resultant stresses on a plane inclined at 30 degree to the axis of minor principal stress. Okay, I'll write this line so that you can understand. Determine the normal, tangential and resultant stresses on a plane inclined at 30 degree to the axis of the minor principal stress. So first we have to locate the axis of minor principal stress. Okay, that is our first job. So after we find the minor principal stress, then again we can find this angle. Okay, so now how can we find the minor principal stress? So we will draw the diagram. Here is no shear stress, so we will simply draw the Mohr circle and we will find the minor principal plane, minor principal stress and the axis of the minor principal stress. So first we will draw a coordinate system. So from here we will take, this is 50 Newton per millimeter square, this is 100 Newton per millimeter square, and because the two diameters, one point will be having at 50 Newton per millimeter square, another one will be at 100 Newton per millimeter square, both are tensile is given, so along same direction, so we have to take 1 centimeter in such a way so that we can have enough long diameter to draw the circle, so that the diameter does not becomes very small. The diameter should be as much as large as possible, otherwise the circle will not be properly visible and properly measured. So if we draw a 5 centimeter long um, diameter, then let's see what happens. See, we need a compass, but here we will just try to make it. So first of all, we have made an angle which is not 90 degree, but it should be 90 degree. While you are doing it, you must take use of your instruments and draw a perfect perpendicular lines. So we will take as the scale will be 1 centimeter represents 10 Newton per millimeter square. So that means 100 Newton per millimeter square will be represented by 10 cm, and 50 Newton per millimeter square will be represented by 5 centimeter. So now as because this diagram is not adequate enough, so we will draw again. And everything should be on first and second coordinate only. So we will take the axis as much as left possible, say like here, and it will be up to 10. So we will mark this 10 here and another 5 over here. So this point OA, this point OB. So here OA representing 100 Newton per millimeter square stress, and this OB is 50 Newton per millimeter square. Okay, so now we have got 2 points which are at 180 degree in the Mohr cycle. So we got the diameter. So if we bisect it, we'll get the center. So this is center C point. Okay, now if we draw the Mohr circle of stress, okay, you have to draw it with compass. I am drawing it with my hand, but that is not you can see properly good, but I have drawn the cycle so that you can understand. Now, so by drawing it, we have drawn the Mohr circle. Now, what was the question? The question was to find the principal tensile stresses at a point across two mutually perpendicular planes are 100 Newton per millimeter square and 50 Newton per millimeter square. Determine the normal and tangential and resultant stresses on a plane inclined at 30 degree to the axis of minor principal stress. So where is the minor principal stress? Here This is the minor principal stress. Now, if the angle does not set clockwise or counterclockwise, so in such case, you can take in any direction you want. So the angle is at 30 degree. So the angle is at 30 degree. So you here on the Mohr cycle of stress, it will be at 60 degree. So either you go counterclockwise 60 degree, or you go clockwise 60 degree. Now this point, when you get, you just draw perpendicular. So when you are going counterclockwise, you get this point, say this is D. When you get clockwise, you get D dash. Now this point can be denoted as E. So when you are taking clockwise, then your tangential stress is how much? D E. And normal stress is O E, and resultant stress will be O D. When we take the angle counterclockwise, then the tangential stress is E D dash, and sigma n becomes OE, sigma r becomes O D dash. Now you have to measure how much centimeter, then multiply that centimeter value, so will be equal to length of DE into, we have taken 1 centimeter equal to 10 Newton per millimeter square. So length of DE in centimeter into 10 Newton per millimeter square. Similarly, this is also length of OE in cm into 10 Newton per millimeter square. And similarly, all these have to be multiplied with 10. Okay. So now we'll go to the next chapter. I hope it got clear to everybody, and I have sent some study material in your Google Classroom. Lot of solved examples are there. Go through them. I hope the thing will be cleared. Give some time to self-study. Now we will go to our next chapter. We will learn how to find out the shear force and bending moment. So our next chapter is shear force and bending moment. Now, before we go deeper in the chapter, we need to know the difference between bars and beams. Bar are those which takes compressive load, and beams are these components takes bending load. Okay, so when the same component is used for taking compressive load, we call it a bar. When that same component is used for bending load, then we call it a beam. Suppose we have this component over here, we place it this way and we apply load on the top. So then it will work as a bar, and when we place this component at this way and apply load on the other end, then it will be using taking bending load, and that will be working as a beam. So I hope the difference between bar and beam is clear to you. Now there are different type of beams are uh, available depending on the situation at they are placed or bending or loading condition. Depending on the condition of the beam, there are different types are there. The first type is cantilever beam. When one end of beam is fixed and the other end is free, so in such case this type of beams will be called cantilever beams. The second part second type are simply supported beams, so simply supported types. In that case, these beams will have support at two ends. They are simply placed over two ends or two supports. So these are called simply supported beam. Now next there is another type. In that case, some portion of the beam is overhung from the support. So this portion is overhung portion. Beyond the support. So this type of beam are called overhanging beam. Now there are fixed beams. When the both ends are rigidly fixed, then they will be called fixed beam. And the other types will be called continuous beam. When continuous beam, when the number of support is more than 2, then we call it continuous beam. And there are some combinations also, like if some portion is taken out beyond the support, it has number of support more than 2 and still some portion is beyond the support, then it will be a combination, and then it will be called overhung continuous beam. That is a type of combination. Okay, I'm not going into that. If the number of supports are more than 2, so it may be 3, maybe 4, maybe 5, it will be called continuous beam. Now there are different loading conditions. We will learn types of load. When we see the load is only concentrated at a point, then this type of loading will be called concentrated or point load. Concentrated or point load, because the load is on a point. Now, when the load is uniformly distributed over a certain length, then it will be called uniformly distributed load or UDL. Uniformly distributed load. So this uniformly distributed load will be denoted or will be expressed as W Newton per meter. Okay, so it is denoted as such that force per unit length or load per unit length. In this way, this uniformly distributed load is expressed. Now there is uniformly varying load. Okay, this needs support. So when the load is uniformly varying, here you can see gradually increasing from 0 to up to certain value. So this type of loading is called uniformly varying load. Okay, so is this page clear to you? Cantilever, one end fixed, other end free. Simply supported, both ends are just supported. Overhanging means there will be some portion hanging out beyond the support. This is fixed beam, both ends are fixed. This is continuous beam having more than two support. Now type of loading, loading at a certain point, concentrated load. Loading is uniform per unit length, W Newton per meter. This is the unit. So this is be called UDL or uniformly distributed load. Here the loading is varying uniformly at a certain rate. So in this case it is called uniformly varying load. So it is discussed, it is expressed by from 0 to W Newton per meter. So at this end it is 0, at this end it is W, or it might not be meter, this is just W Newton. So it will be, it varies from 0 to W with respect to the length. Now, so in this case, at a distance of x, at any section, if at a section say xx, if you want to find out the loading at section xx, how can you find out? For the whole section, the distribution is as such, W minus 0 by L, if the whole length is L. So for L length, the change is W minus 0. So for x length at xx, the load will be W minus 0 into x. Very simple way we can find out the loading at any section. However, we will solve problems on it. We will discuss more elaborately. Now, we learn about shear force and the sign convention and bending moment and sign convention of bending moment also. So first things first, we need to learn shear force. Suppose we have a bar having loading condition just like this. This is at A section, this is B section. This bar is simply supported over two rigid supports. At the center or the midsection, there is a load 1000 Newton. The bar is of uniform cross section. Now, in this section, if you are asked to find shear force and bending moment at any given section, so you have to take any section. We call it, say, X section. Now, the shear force is the resultant vertical force acting at that section. Okay. Now, the resultant force acting on any of the parts normal to the axis of the beam is called the shear force at that section XX. I am saying it again. The resultant force acting on any one of the parts normal to the axis of the beam is called shear force at section XX. So we are looking at the section XX. We need to find the shear force at section XX. So we will just take any one of the side, either left side or right side. So in complex problems, we always choose the side which is having less number of forces. It will be helpful, but that is totally on your choice. So you have to take any of the side of your given section. So here, this XX having two sides, left side and right side. Now, if you look at this problem carefully, at the center there is 1000 Newton. So this reaction force on A and B will be just half of this applied force. So this will be 500 Newton. This will be again 500 Newton. Okay. Now, these 500 and 500 are the reaction forces at the supports A and B. Now you just take any of the sections. Okay, the result will come same. Now, if you take from the left hand side, the resultant forces to the left of the section is, you see, there is no other force except this one force, 500 Newton upward. Okay, so on the left hand side, the shear force is 500 Newton upward. If you look on the right hand side, you start from this end. So up to B to C, there is no forces. So from B to C, there will be 500 Newton upward, and at C point here, the resultant force become 1000 Newton minus 500 Newton. So 500 Newton downward. So at section XX, we get on the left hand side 500 Newton upward, on the right hand side 500 Newton leftward. So in both the cases, whether you take left hand, whether you take right hand, the resultant force is 500 Newton. So you can say at section XX, the resultant force along the direction perpendicular to the axis of the beam is 500 Newton. Then we can say the shear force value at section XX is 500 Newton. Okay, we have not said any word about direction, about sign convention. We are just saying that the shear force is 500 Newton. Now we have a sign convention. When there is a beam and at any section, because of the resultant forces on this beam, the beam will try to shear off by this way. That means the left hand side tries to move up, the left hand side tries to move upwards, and the right hand side tries to move downward. In such case, the shear force is positive. Okay, so you will find if the forces on the left, resultant forces, resultant force of the forces on the left is trying to make a clockwise movement, then left hand side tries to make clockwise, right hand side also tries to make clockwise, then it is a positive type of shear force. Similarly, if the opposite happens, it will be negative shear force. So now if we want to draw the shear force diagram of the same problem, then we will draw like this. This is the beam. We'll extend this end. We'll draw a neutral line. We'll draw a neutral line. Now, if we draw from the left hand side, so the shear force is positive. Shear force positive. So at section, so as you can see here, there is a load at the center, 1000 Newton. So if we start drawing from left side, then when the section XX is up to point C, just before point C, the shear force will be positive, because the left, when the XX is just before C, imagine in your head, try to visualize, when this XX section is between A to C at any point, then the shear force is positive and the value of shear force will be 500 Newton. So we will draw, this this type of diagram. Shear force is not changing. At point A it is 500 Newton and up to point C. So this is A, this is B, and this is point, this is C point. Okay, now here this much will be plus 500 Newton, and if you take the section between C and B, just try to imagine you are taking a section between B and C. I'll draw it in we call, say, section YY. Section YY is taken between B and C, at any point between B and C. Now if we take right of this section YY, then you will find here there is a load 500 Newton, here is another load 500 Newton. So now you look, this 500 Newton is trying to rotate or to shift this right hand portion, this right side of this beam to move upward, which is negative. We have said that when it becomes positive, when the right side of the section goes down, then shear force positive. Here, the right side of this YY section is trying to shift upward. So the shear force will be negative. How much negative? 500 Newton. So up to which length it will be negative? Up to point C. Between this B point and C point, you take any section. If the YY is just before the C here, then also this 500 Newton will be trying to move this section upward. So that will be a negative. So from B to C, it will be minus 500 Newton shear force. So the diagram is as such. You have to draw it in hatched section so that it can be understood that the shear force then from A to C region is positive. At C it changes sign, and from C to B it is negative. So this is how we draw the shear force. Okay, any question on this concept? How to find out shear force? Is there any question? Avronil, is it clear? Most of the people are silent in the class, but those who are listening, please give me some reply in the chat box. Okay, so we'll stop here today as the time is time is already done. It's 12:51. So we'll stop here today, and in the next class we will continue.